So we continue with the discussion of motion of the situation in which a infinite solid plate moves in the x direction with the velocity v. We have already deduced that u is dependent on z and t and not on x or y, and this has been derived by virtue of this part of the continuity equation in which other components vanish and we have partial derivative of u with respect to x. So when we integrate it, then obviously u is equal to some constant as far as x is concerned. So it will be, if it has to vary, then we deduce that it may depend on z or t as written here. So that's one important result that we have. Then from the y momentum equation, we are first taking the y momentum equation, we take the z momentum equation, the z component, and then finally we will also take the x component of momentum equation, and combining all these we will have the result of this problem. From y component of momentum equation, the only thing that we derive from there is dp by dy is equal to 0, the partial derivative, so which means that again the pressure does not depend on y, and therefore we have, if p is dependent at all on something, we will have p is equal to p of z or t, just like u. And similarly, the z component of momentum equation finally reduces when we substitute the values into the z component of momentum equation. We obtain partial derivative of p with respect to z is equal to minus rho g. All other terms vanish, they drop out. So this is non-zero term, and from this then we come to the first equation of momentum that we write, and that is in the x direction. So the x component, or the component of momentum equation in x direction, if we write in totality, is this, as you can see. But these terms also render us this result, that since we have seen that u can possibly depend on either t or z, possibly, the du by dx is 0, the partial derivative. Du by dy is anyway 0 because no motion takes place in the y direction, and partial derivative of u with respect to z is also 0 by virtue of assumption 2, which we have listed earlier. dp by dx is also 0, so because pressure does not change with respect to x, and there is no component of gravity in the x direction. The only component of gravity is in the z direction, and that is also in the downward, so that will not contribute anything when we are considering the x component of momentum equation. On the right hand side, the other thing, that the terms that are associated with the viscosity is mu into second order Laplacian acting on u, the velocity component in the x direction. Since du by dx is 0, so this is also 0. This is again from assumption 5 as it was here, and the only non-zero term that is remaining is this one. So you have seen that there are only two terms that are non-zero, they do not vanish, and this whole component reduces to this partial differential equation. As you can see, it's a linear one-dimensional equation, very familiar to mathematicians. It appears in many problems of engineering, physics, mathematics in different forms according to the different problems that are being considered. It is even appears in heat also. So, and it is known as diffusion equation. We call it normally the diffusion equation. So, combining this, taking the row on the right hand side, we will have mu over rho, and that we write as nu. Nu is kinematic viscosity, while mu is called the coefficient of viscosity and rho is the density. So this ratio is defined as kinematic viscosity, which reflects the particular behavior of the viscous fluid that is under consideration. And so the diffusion equation, we need to solve this together with the value of P as well as the value of U that we derived earlier. When we integrate dP by dz, then we have which is equal to, from the z component of momentum equation, we will obtain P is equal to minus rho gz plus some constant of integration, and let us say this possibly depend on time. Well, this is a reflection trying to show and making a remark that this is a diffusion equation. Therefore, what we can do is, to solve this, we try to take or convert the two variables z and t into one independent variable. And the procedure that we use is what we call as similarity solution. The advantage of similarity solution is then that results derived from that can be applied to independently to various problems without a specific consideration to this particular problem that we started with. When we try to integrate the diffusion equation, we obtain finally U is equal to some constant of integration C1 into 1 minus air function, what we call as air function, z over root nu t by 2 into multiplied by 2. The air function is defined as this. So as mathematicians, you are all familiar with this function, and the tables of this for different values of eta, this is the Greek alphabet eta, and it is used for, as you can see, for this number. So the solution we will have for this problem appears to be this one, and we leave that with that, and we will stay with this solution. We solve it for various values of eta, and there are a lot of tables that are available because the eta function has to be many times, it has to be computed numerically. Most of you will be familiar with this function, so this will be the solution for the particular problem at hand.